The lightning speakers, remember when the person before you is talking, you should come up and be waiting, because the time, if we're waiting for you, it's coming off of your time. Everybody has 5 minutes, and Esben, go.
Yes, thank you for the opportunity to come here and give a little update on Scikit-Mol, which is RDKit integration in scikit-learn. So there have been some updates and new features since I gave the last lightning talk on this topic 3 years ago. So just a brief summary if you're not familiar with the project. It started actually at the hackathon in 2022. The basic idea is we combine the scikit-learn estimators, the base classes there, and turn some RDKit functionality into something that is compatible with scikit-learn and their infrastructure, so that it gets easier to build together with these two good toolkits. So a quick recap here. We show how you can easily use our smiles to mole transformer from Scikit-Mol and a Morgan fingerprint transformer together with scikit-learn rich regressor, and you can get a model, and you can then start to fit it using just lists of smiles. And that means suddenly your final model object is self-contained. It contains both the featurization and the model itself, so you don't split this up, and you can always go and look at the parameters that were set, and you don't get in doubt about this. And that also allows for suddenly access the hyperparameters of your featurization using optimizers that are compatible with scikit-learn because we have everything in the same model. And because we are compatible also with scikit-learn, we can also start to use their pipeline and other classes to build more complex model. Here to the right is shown a single one that combines Morgan fingerprint transformer with a molecular descriptor transformer, some polynomial feature expansion and feature selection using a random forest before joining these two things together in the final model, and that can maybe give a better model, and it shows just some of the creative solutions you can quickly build. So under the hood, there have been a lot of maintenance and project improvements, nothing you see really in the feature space and such, but it's also important for a project to do this. So there's been a new online documentation, switched to RDKit generators. The original one were giving deprecation warnings. A conda package was developed, UV build framework, and improved parallelism with job-lib. Another interesting feature that was added with a contribution was this pandas input and output support, that you can set the transform for pandas on scikit-learn objects. And it's very, very handy actually when you do feature importance analysis and other things, that you get out the pandas data frame from your pipeline, and you can see what columns are used where via their names. And these column names are actually also checked during prediction for consistency. And it's also then possible suddenly to have a feature matrix that is larger than your model have, because you can use what features the model needs to quickly filter out before you do the prediction. Another thing is also the safe inference mode was added, because sometimes problematic molecules or smiles can't be sent for the featureizer or the transformers that will then blow up the whole batch you're trying to predict. And during training and testing of your model, you're in charge of that. You can build out your data set, but once you deploy it, users or generative AI or whatever can start to give wrong smiles. So now all the Scikit-Mol objects, they handle these false objects gracefully, but scikit-learn estimators doesn't. They need to be wrapped in this safe inference wrapper that understands that you get a masked NumPy array rather than a standard NumPy array. And then also we added some feature-based applicability domain estimators from the MLChem-AD project that was integrated into the kind of API and can also be used together with the other transformers. So we have a transform that returns the original score, but also predict that returns 0 or 1. Are you within or outside of the configurable boundary? And also there's a score transform which gives a soft boundary. So there's a range of various applicability domain and estimators. So in conclusion, it's the Scikit-Mol is this hackathon-initiated project, and new features are still being added with contributions from individuals from a long range of industry and academia. There's plenty of notebooks and examples to get you started, and you can use pip conda to install it. So thank you. So yes, thank you very much for the second opportunity to present a little project that I think was interesting maybe for somebody, or could be an inspiration. So it's about a pdChemChain, which is some interactive links for chemistry data processing. So pipelining tools, I'm a little bit mixed about this. You know, there are hundreds of pipelining tools out there. There's actually a GitHub trying to collect everything, and it seems like they just proliferate all the time. And I guess it's because different people have different needs. Do you want to water your garden, or do you need to transport an industrial amount of oil, or do you want some flexible solution? Or maybe you want pipes that doesn't even treat water, right? So I didn't find one that fit me exactly right. So what I wanted something that was easy to use in Jupyter notebooks and other these kind of interactive coding environments. So I could have short code test cycles and explore data analysis with it, and some kind of stepwise application of each step and look at the output. So I thought about how to do this, and I ended up with a couple of simple choices for the API. And the first one is you have your link, and it takes in a pandas data frame, and you get a data frame out. Nothing else, no error data frame or nothing. It has to follow this. The second one was we need to expand this. A single link is not interesting. So summing links gives a chain, and a chain is also a link and can be summed with other chains or other links. So that's also something we can do. We can add two links together with a plus operator. We get a chain, and that also takes the data frame in and put it out. And we can use the sum a list, or we can concatenate them, or we can do that. So we can construct chains from links. But then, you know, somebody says that Python notebooks are really the fast food of software development. They can be good, but if you only do that, then it may not be good for you in the long run. So there's also added this auto-documenting and auto-configurable feature that you can always get the parameters of a chain and its internal links, or the links, and you can also then instantiate the same object or clone of that from these parameters. And then suddenly there's not far to actually save a YAML file and be able to run it from the command line, and you can then start to use it on the server when you're satisfied with what you have set up in your Jupyter notebook. So I worked hard to try and make it as simple as possible to add new classes. So there are some base classes that you subclass. They have to be data classes. And then you simply need to override for this one, the row apply, where you get in a pandas series of the row, and you can do whatever you want, and then you return the row. And if you do that, then suddenly you get a lot of the infrastructure there. There's also one that works on the whole pandas data frame, but then you need to take care of the error handling yourself. So some other features, error handling of rows. It doesn't explode if something goes wrong in one of the links at row number 8,435,235. There's a growing link library, and there's also a little bit advanced routing and high performance possibilities with some compound links. We can route the pandas data frame through different internal links or chains and concatenate the output, or we can chunk up the data frame in smaller things to save memory, or we can send it out to different processes in parallel. So it's open source, and now we have one more pipeline. Thank you for your attention.
Yep. So can I have the microphone? So yeah, hi. Now it's actually my turn to tell you something about what we do here in UCT Prague. So I'll be talking about an ecosystem for Cheminformatics that we sort of unwillingly developed when I was doing my postdoc in Leiden with Gerard over there. So we all see these problems every day. So you have to deal with poorly documented code that's poorly structured. You have to do a lot of work to just basically run it or understand it to some extent. And you always run into errors when you try it on your edge cases. So you can see that the people who developed the code maybe didn't test it. So there is a solution for that. So which is this FAIR methodology, where you basically try to approach your data in a findable, accessible, reusable, and interoperable way. So that's what we also try to do when we develop the software packages. So actually, I was already presenting this slide last year. So if the window from presentation to implementation is 3 years, then I'm on year 1. So right now we're still kind of developing this and playing with it, but it's already open source, and we use some parts of this workflow. So basically the idea or basically the angle that we approached this problem from is that we developed some notion of like a common chemical storage API in Python. So what's underneath this, it can be a database, it can be a data frame, it can also be a REST API, it can be your chemical registration system that you like. And then basically we developed our tools to use this storage system. So we have different packages. Jagex is for de novo generation, QSPRPret is for QSAR modeling. It's very close to what we just saw with Scikit-Mol. So it also has now implementation of scikit-learn pipelines as well. And Spock is a new package that we're still developing. That's not really open source yet. This is for structure-based dark design and docking. So I will show you some examples here. So this is how the storage works. So you basically initialize it. Here it's a pandas data frame. You can basically give it some metadata. We also, it was already said here that parallelization of some tasks is important. So yeah, you can use standardizer or identifier, but if you already hook up to a registration system that does it for you, you don't have to supply this. Then you can basically save it with all the metadata of the storage, so of the molecules that are in your subset. And then you can also load it from the file, and you can see that all the metadata that you have added as attributes is going to be there. And you can also do smart search. And this is actually done in parallel, and we're implementing also different APIs for doing this parallelization, not just with multiprocessing, but also with Dask. So you can do more powerful stuff. For example, like docking. So this is our definition of basically our wrapper around Autodock Vina, that you can just define your docking protocol like this. And then you can drop the storage into this docking protocol. So it understands the storage API. So it can dock it. It can use multiple CPUs or actually a Dask set of Dask workers. That's not implemented yet, but we're playing with it and it's possible. And thanks, Greg, for that tip about the binarization. So, and then you can basically from the storage, you can get your complex like this, just 2 lines. So yeah, you can check it out on our GitHub. Thanks.
So, hello everyone. Today I'll talk here about my project related to a new line notation. I also have a poster about it. I'm gonna have to be really rapid today, so if some things are unclear, just come to the poster. Also, the slides contain a lot of background information, which I will not even say out loud. Many people visiting my poster have asked me the same question. So actually, why do you even do this? Why to do this breadth first? And the reason is twofold. First reason is that we are interested in quantifying similarity of molecules directly from the string. The older people in the audience here maybe will have heard of Lingos. So what we care about is to have n-grams that have the atoms that are close in the graph also close in the string. The second reason is nowadays people are training CLMs that's like comparable to PLMs. So you get a bunch of line notations, you get a bunch of strings, magic machine learning happens, and suddenly the model learns various things that are not directly in there. Famously, in proteins, that works very well. ESM is an example of such a model. So how do we make this? How is this possible? We make use of the fact that just using the degrees in sequence in order, we can reconstruct any tree. So that works as follows. Here is a degree sequence. How do we reconstruct the tree from this? So the first one is tree that has 3 children. Then we expand those nodes, we put the degrees there, and again, we know how many children it has and so on, until we have all the numbers and we have our tree. Now, this is not possible for when we have cycles, so we use the same trick as is used in smiles, so we just add ring opening and ring closure operations. Now, all we need to do is add chemical tokens in there, and now we have a line notation. So we use smiles like way to do it. You can see it here. It has the same bracket notation. Only difference is that the bond here always is the bond to the parent, and the number behind is the degree of that specific atom. Okay. So here is an example of it. It's the same graph. Now I just added these atom tokens on there. And here on the bottom, you can see what this blinks actually looks like. So it's not that much longer than the smiles. There's also a nice implementation. You can see here it works even on tricky cases like Cubane. You can find it on my GitHub. You can also see the size of it is quite okay, a little bit higher than smiles, but not much higher. So now we apply it for building CLM. I'm just gonna skip this here. Yeah, we use an LSTM to do that, and here are the settings of the LSTM, and you can see here we generate with this LSTM 500K molecules. We have really nice fresh ChemNet distance showing that it really learned the distribution nicely, even a little bit more nicely than the smiles LSTM. Now, from the LSTM, we can also take embeddings. So we just take the final cell state and we use that as featurization of our molecule. And we apply this to a QSPR task. Use Ocelot ML because I didn't want to use MoleculeNet and be criticized for it. This is more challenging on a set. And so here you can see the results. What we care about here is mainly green versus red. So green is the Blinks embeddings, red is the smiles embeddings. This is R squared, so higher is better. And main conclusion here is it's slightly better, but in the end, actually, the true baseline of chemical fingerprints is still better. And this is, of course, known for learned embeddings, but the main conclusion there is that actually the LSTM is able to learn the same kind of information about chemistry as it's able to do from the smiles. The token distance and topological distance are paired in a bit more natural way. This is probably where the distribution learning advantage comes from. The implementation is available, so definitely play around with it, and I will be happy to hear your feedback on it. And that's all, so thank you.
Okay, thank you very much. Great. Good. Okay, so hi all, I'm Mher from Dinova, and I would like to talk about null retrosynthesis approach we call Synthony. So to provide us a context, retrosynthesis is the process with which you identify your target, how to synthesize your target molecule, what kind of pathway you have. And it's usually represented by tree, where the leaves are reactants, you have intermediates, and you also have synthons. I've mentioned them because as from the name, you might think they are relevant. So to remind, synthons are just transformations of reactants that are present in the target molecule. So for this particular example, the left reactant has iodine and it is transformed into nitrogen. For the right, it's basically the same. And we have seen many approaches with retrosynthesis and ML. And the standard approach would be to develop one-step retrosynthesis like disconnection approach and recursively apply it so you can find the pathway. So for example, for this particular molecule, you apply one-step retrosynthesis. You find that one of the compounds is actually in commercially available database. The other one is not. You recursively apply it and hopefully find the complete pathway. And more often than not, you actually don't find it. So actually, to circumvent this problem, we came up with an idea that we might be able to find necessary reactants before actually constructing the retrosynthetic pathway. So it's kind of like picking out what kind of Lego building blocks you need to build your house in advance, rather than like deciding from the house itself. And to do this, here's the general approach that we have adopted. So first, we have a database creation of Synthon. So we pick out a reaction database as well as a building block database and create Synthons from that. The second step would be to do superstructure search on the database for our target molecule. The first step would be to find combinations of all Synthons that actually make up the whole target molecule without any overlapping. Then we'll combine those, then we will rank those combinations and eventually build the full retrosynthesis tree from bottom up. And all of this is based on RDKit as well as C++ components. So if you would like to actually have experimental setup where you can try some custom C++ scripts with Python embeddings, it's actually available in Google Colab, where you can do it in 2 minutes. So you can just look at the presentation. So to go a little bit into details, the database creation, we took USPTO50K as reactions. We took USPTO full as building block. Then we used RDKRL to actually extract the templates. After that, we divided the templates into Synthon templates, where the Synthon template just corresponds to each reactant participating in the reaction. And after that, we mashed all the Synthon templates to whole reaction building blocks to actually generate Synthons. The second step will be superstructure search, which is basically the opposite of substructure search, where you try to identify which molecules from a database are contained within your query molecule. And the next step would be to define our problem as the exact cover problem, where we ask for a given set and the collection of its subsets. Are there sub-collections where you can exactly cover the whole set without any overlap? The next step would be to rank all those combinations. We use frequency-based, where we identify the frequency of the templates. The higher, the better, it would rank higher, and just apply more ML stuff to actually make it more fine-tuned. And the last step would be just to build the tree itself from bottom up, basically from leaves to a root. We have some preliminary results on the single-step retrosynthesis. We can see that it has quite good results on top K accuracy, where top K measures for a single-step retrosynthesis if your predictions contain true reactants in their top 1, top 3, or top 5, etc. predictions. But there's a nuance, because our approach implicitly only gives predictions for the building blocks that are in the database. It's not very fair to compare our methods where they consider all possible hypothetical building blocks. And when we give this information to our approaches, we can see that they bump up quite considerably. But I actually don't think this is a fair comparison either. And if you would like to know more, I'm happy to discuss in Discord or a poster session, because we have also posted on this. So thank you very much. This is all from me.